The name alternating series refers to series whose signs alternate between positive and negative. We start this with the alternating series test. It starts out saying if the alternating series, the sum as n goes from 1 to infinity of negative 1 to the n minus 1, now that's what's going to make it alternate, times b sub n, which is equal to b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5 minus b sub 6 plus ... and so on forever. If that series where the b sub n's are greater than 0, so here's the deal. The b sub n itself is a positive value. It's the negative 1 to the n minus 1 that's going to make the terms alternate in sign. But for this series of videos, b sub n is going to refer to a positive number. If this series satisfies two criteria, one, that b sub n plus 1 is less than or equal to b sub n for all n, that is to say it's decreasing in magnitude, and two, the limit as n approaches infinity of b sub n is equal to 0, then the series is convergent. So when you perform the alternating series test, you must perform two little subtests. One of them, you've got to show that the series is decreasing in magnitude. And we've got to show that the limit as n approaches infinity of the terms is equal to 0. Let's look at a diagram that's useful in understanding some of the concepts in this series of videos. Supposing starting at 0, if we add the number b1, of course this s1 then is b1. And then if we subtract b2, now that would be really adding the first two terms, right? b1 minus b2 is just adding the first two terms. Then we're back over here to the left near 0, and that would be s2. Adding s3 would bring us over to the right, but not quite as far as s1 because I've subtracted b2, add b3. And what we see is that all of the subscripts, s2, s4, s6, are to the left side of the picture. S5, S3, S1, those are all odd partial sums. Those subscripts are to the right of our picture. And then the actual sum, S, is going to be somewhere between all of those. If you kind of stare at that for a bit, it'll make sense. Let's look at the proof of this test. Even partial sums are given by, well, S2, as we just saw, is B1 minus B2. And that's positive because b2 by assumption is less than or equal to b1. Well, I said it was positive. It's greater than or equal to 0 is what I should have said. S4 is equal to S2, and then we're going to add the next two terms, b3 minus b4. And that's greater than or equal to S2 because, again, b3 is less than or equal to, b4 is less than or equal to b3. In general, S sub 2n, an even sum, is equal to S sub 2n minus 2 plus B sub 2n minus 1 minus B sub 2n, and that's greater than or equal to S sub 2n minus 2 because we took S sub 2n minus 2 and added a positive value to it. Remember that b sub 2n is less than or equal to b sub 2n minus 1. Well, folks, S2 is greater than or equal to 0, S4 is greater than or equal to S2, and so on. S sub 2n is greater than or equal to its predecessor, S sub 2n minus 2. We can write this down as a series of inequalities. It follows that 0 is less than or equal to S2, which is less than or equal to S4, which is less than or equal to ... which is less than or equal to S sub 2n, which is less than or equal to ... Lost it there. So the sequence S sub 2n is increasing. Also, S sub 2n can be represented as S sub 2n is equal to b1 minus the quantity of b2 minus b3 minus the quantity of b4 minus b5 minus the quantity of, well, ... minus the quantity of b sub 2n minus 2 minus b sub 2n minus 1, I wanted to squeeze one more term in, minus b sub 2n. Now this comes from, if you look back at our original expansion of the series, basically grouping up b2 and b3 and factoring out the negative. Then that goes negative. Likewise with b4 and b5, factoring out the negative, grouping them together. What we have though is, since the terms are in magnitude decreasing, b2 minus b3 is positive, b4 minus b5 is positive, b sub 2n minus 2 minus b sub 2n minus 1 is positive, and b sub 2n is positive. Okay, what's the point of all that? S sub 2n is b1 minus a bunch of positive numbers, which means that S sub 2n is less than or equal to the first term b sub 1 for all n. So the sequence S sub 2n is bounded above. What we have then is a sequence that is increasing and bounded. So the sequence of even sums S sub 2n is convergent by the monotonic sequence theorem. We're sure getting a lot of mileage out of that theorem. Now, suppose that we call the limit as n approaches infinity of S sub 2n S. If we then turn to the odd partial sums, we can consider the limit as n approaches infinity of S sub 2n plus 1, an odd subscript, which is equal to the limit as n approaches infinity of S sub 2n plus b sub 2n plus 1. Then here we've got that S sub 2n is a partial sum, and b sub 2n plus 1 is the next term. Assuming both of these limits exist, well, we don't have to assume it. We've just shown that the limit as n approaches infinity of S sub 2n exists, and the limit as n approaches infinity of b sub 2n plus 1 is 0 by assumption. Remember, there were two conditions when we stated this. Not only were the terms getting smaller in magnitude, but the limit was 0. Now we're using that fact. And as we said, the limit as n approaches infinity of S sub 2n is equal to S. Now, we started out this particular expression as the limit as n approaches infinity of S sub 2n plus 1. We have now shown that the odd partial sums also have a limit of S. This would imply that the series is convergent. And that concludes the proof.